Well, good morning, guys. Thought I would, I normally don't do this, but I thought I would take a video of my solutions. I really do hope you're looking at this and you don't just check the key. These solutions, I want you to really know this. There are more than one, more than one way, zillions of ways you can do lots of these problems. What I'm doing is what's popping into my head. If more than one thought pops into my head, I may work a problem multiple ways just to show you and emphasize that. So as you're looking through these, the goal is to get them simplified. All right, so in the end, if your answer looks like my answer, then you're in good shape. The path that you get there, you may do something more efficiently than me. You may do something that takes a lot longer than me. That's okay, as long as you're getting there. So I'm gonna talk about a lot of these processes. Also, there is a page in the book that talks about a strategy for simplifying trig identities. I think it may have a picture of Kevin Hart kind of doing something like, or something on it. And it's a few pages back. So if you thumb through the book, there are some guidelines, and those guidelines, I'll talk about those individual principles. But if you're ever having any trouble, try those strategies. I'll try to refer back to them and mention them in the video as well. But they're pretty good strategies when you get stumped and you don't know what to do, or you're wondering, have I simplified this enough? Because it's not as straightforward as normally when you see the word simplify, you just think PEMDAS, but it's not quite the same, all right? Because you're gonna have all these weird trig identities and you're gonna be thinking, wait a minute, what in the world, how does PEMDAS work into this? So anyway, I think the best experience for you will be practice. The more you do with these, the better off you'll be, and I think you'll see that. So hopefully you have no issues, but if you do, please thumb through these problems and see what you can do on the ones that you had trouble with, and maybe it'll put you in a good spot. All right, here we go. Oh yeah, and here's your dumb dad joke for the day. What does a nosy pepper do? It gets jalapeno business. All right, guys, so we're looking at page 639, and your homework was to do a bunch of odd problems on that page. So again, if you're looking at this today, hopefully when you did these problems, you looked in the back of the book or whatever, and you saw that you were right on a lot of them. If you're not, no worries. Maybe just start following along with me and getting the idea. But if all you're doing is watching this video to see my process, you're going to learn a little bit from it, but it's certainly not going to be as much as actually trying to work through some of these on your own. So anyway, bottom line, we're going to just start attacking these, and just know this too, like I mentioned earlier, there's more than one way to do each of these problems. Well, maybe not every one, but there's more than one way to do a lot of these problems. So what I'm doing might not even be what they did in the solutions in the book. And that's okay. This is just what's popping into my head first. And sometimes I'll show you multiple ways to do the same problem if it feels like it's necessary. So anyway, first thing, I'm going to look at number one. It says, what is the sine of alpha times the secant of alpha? And the question for all of these is to simplify. So I'm not going to write the word simplify for all of these. I'll just write it this once. But again, that's what they're asking you to do. And remember, simplify normally means to do PEMDAS, go through those processes of parentheses, exponents, multiplication. But here, even though there's a little bit of that, it's not as straightforward. So if you have any issues on this, there is a worksheet that I want you to, or not a worksheet, but a page in the book that I gave you. And I'm going to go find it real quickly. I want to say it's not right where it should be. For some weird reason, I have it in a wrong place. I believe it's page 45. And there's a picture of Kevin Hart at the bottom. But on 45, there are these 8 rules for simplifying trig expressions. And one of the things that, and you'll see them as you read through them, you'll start noticing that I'm doing some of these things today. So as I do them, I might point out, hey, this is what my brain was thinking, so that you'll know. But it's a great troubleshooting list of things to do when you get stuck. And one of them I do a lot of is number 2. And number 2 on your list is converting to sines and cosines. And since every trig function can be converted to sines and cosines, it enables you to rewrite it and then a lot of times cancel stuff out, simplifies real nicely. So look at this one. I have a sine and a secant. Well, secant, because I really don't know what I get when I multiply those together, I just get this. I'm going to rewrite the secant part. I'm just going to bring down sine, and secant is a reciprocal with cosine. So it's the same thing as 1 over cosine alpha. And then now I end up with sine alpha over cosine alpha. And we know from our trig identities sheet that sine alpha over cosine alpha is tangent alpha. And if you didn't know that, now you do, but it is on our identity sheet that is listed in Schoology. I put an extra copy up there. We need to know that that's tangent. And by the way, cosine over sine, because it's a reciprocal of that, would be cotangent. All right, so let's look at number 3. Number 3 gives you the tangent of x over the sine of x. All right, so again, tangent over sine, that's not an identity that I have, but I do know that tangent, because I just did it here, tangent's the same thing as sine over cosine. So I'm going to work this one to the right as opposed to down. Tangent is the same thing as the sine of x over the cosine of x, and then that whole thing is divided by sine of x. All right, well, when I'm looking at this, I really don't like to have fractions inside of fractions, so I'm going to think, what could I do to take the top and divide by the bottom? Well, we've learned to divide by something, you basically take the top part and you leave it alone and you multiply by the reciprocal of the bottom. And the reciprocal of the bottom is 1 over sine of x. And then now what do you see? Now that you're multiplying, those cancel, right? And I'm now left with 1 over cosine of x. And what is 1 over cosine? Well, we know that cosine and secant are reciprocals, so 1 over cosine must be equal to the secant of x. All right? All right, looking on to number 5. All right, now again, these are just the things that popped into my head, strategies that I'm going to use to simplify these. All right, so this one is 1 minus sine of theta times 1 plus sine of theta. And we saw something similar to this in the work we did yesterday when you watched the video. And I don't have, that's not an identity. Now there is an identity, I don't know if you remember, there's an identity that says the sine squared of theta plus the cosine squared of theta equals 1. And we learned that that was called a Pythagorean identity. And this identity, a lot of people kind of get messed up here. They think, oh, well, I've got 1 minus sine squared theta, and that's equal to cosine squared theta. And they make the mistake of thinking, well, if 1 minus sine squared theta is that, then 1 minus sine theta must be cosine theta. And they think that this is true, right? But it's not true. You can't square root each part. It doesn't work that way. You can square root the whole side, but we know that square rooting a binomial doesn't square root each part. So that's wrong. So don't replace that with a cosine theta and think you're okay. There's no squared on it, you can't do it. But what I can do is FOIL it out. And if I FOIL it out, first, outer, inner, last, the first gives me a 1. The outer and the inner, because these are like conjugates, they cancel, right? The positive sine theta and the negative sine theta cancel. And then I'm left with minus sine squared theta. Now that is this. So this I can replace with cosine squared. And you'll notice once you get it down to a single term, like we did in number 1, or like we did in number 3, and here down here in number 5, once I get it down to a single term, I can with a lot of confidence think, all right, I must be done with this problem. Okay? And we typically don't want to leave it as a fraction. And if you say, why not? If you think back on your list on page 45 in the book, the first thing is try to represent the expression in the numerator. Well, that alone suggests you don't want to leave it as a fraction. Okay? So I have employed a rule right here. I used a Pythagorean identity. And using a Pythagorean identity is number 4 on your list of simplifying trig identities on page 45. So you can see I'm already starting to use these rules without even thinking a whole lot about it. Number 7, the question is cosine of alpha. And notice they're changing the letters a lot. That's not to try to mess with you. It's just try to get you comfortable with. It doesn't really matter what letter they use for the angle. I use theta a lot or alpha a lot. But by the time you get to upper level math, they're just going to be using X. It's like everybody kind of gets lazy and they don't even use Greek letters anymore. All right, so right here I've got this, and I certainly don't have an identity that's cosine times cosecant times tangent. I haven't seen that together like this. So I think, well, I'm going to try to change everything to sines and cosines. That's rule number 2 on my list on the list on page 45. So from here on out, I'm going to say rule number 2. Just know I'm referring to that list with Kevin Hart's face at the bottom. So cosine is already in terms of cosine and sine. Cosecant is a reciprocal of sine, so I'm going to write it as 1 over sine of alpha. And tangent is sine of alpha over cosine of alpha. So I'm using these fundamental identities that I know, right? And that's rule number 3. Use the fundamental identities. I'm using them to rewrite everything in terms of sines and cosines. And now look, I can cancel out that I don't know why I put 2 alphas there. I can cancel out the cosines, cancel out the sines, and what do I have left? When I cancel stuff, I'm left with 1s. So I have 1 over 1, which is 1. So that was just a fancy way of saying number 1, the number 1. All right, look at number 8. Sorry, we did number 8 yesterday. Look at number 9. Number 9 is the sine of x over the cosecant of x. And then over here, I have the cosine of x over the secant of x. Now on this one, I'm going to show you the long way to do it, and then I'm going to show you a shortcut. Okay, so the long way would be, well, this is not an identity that I recognize. I'm trying to simplify it. So what I'm going to do is change cosecant right there where it is. This is the long way. Cosecant is 1 over sine, so I'm going to replace that with 1 over sine of x right there on the bottom. And here, this is the long way. I'm going to show you the short way in a second. Here, secant here is the reciprocal of cosine, so I'm going to replace it with 1 over cosine of x right there where it is. Now, what I'm trying to get you to see here is, what would you do to take this and divide by a fraction? Well, you would take the top part and multiply by the reciprocal of that, which is just a regular sine. And what are you left with? Sine squared of x. Same thing here. What would you do? Well, you take the top part, cosine, and you'd multiply by the reciprocal of that, which is cosine of x over 1, or just cosine x, and that gives you 2 cosine squared. Now, this right here is the hard way to do this. And what I want you to see from this is you can really skip that step if you think, wait a minute, a cosecant in the denominator is the same thing as a sine in the numerator. So I could have just taken this cosecant, because it ends up being what? A sine in the numerator. I could have just brought it up and made it a sine x times all of that. And I could have taken this secant, rather than going this route, I could have just taken the secant and brought it up and turned it into a cosine. Because the secant on the bottom is a cosine on the top, cosecant on the bottom is a sine on the top, because they're reciprocals. And that will allow me to jump straight to here and to here. And then now, what do I recognize? That's a Pythagorean identity. As long as sine squared and cosine squared are being added and they have the same angle, they're always going to be equal to 1. All right? And that is number 9. So on to number 11. So number 11 asks me, let me get my paper lined up. Number 11 asks me to do secant over cosine, secant theta over cosine theta, minus 1. Now, to simplify, 2 things being added or subtracted, and one of them is a fraction, means I'm probably going to have to find a common denominator. But before I find a common denominator here, and if I wanted to have a cosine, I would have to change 1 into cosine over cosine, just like I would normally do with the common denominator. But before I do that, I really am not a big fan of the secant. One of my rules is to convert everything to sines and cosines. Well, let me ask you a question. On the problem we did before, a secant on the bottom was a cosine on the top. What do you think a secant on the top is? That's right. It ends up being an extra cosine on the bottom. So if this secant here becomes a cosine down below, that gives me a cosine squared down below, and there's nothing left on the top except a 1. Now what do I do to find a common denominator? Well, if it's the number 1, I have to have the same thing down here as I do up here. So if I'm going to change the bottom by a cosine squared to cosine squared, I've got to multiply the top by cosine squared at all, so that that would still represent the number 1, which it does. At this point, I can add by keeping the common denominator and subtracting the numerators. Now, at this point, you're like, well, how did you know to do this? Well, if you think about your sheet, what does it say on that little list of tricks or rules on page 45? It says add fractions by finding a common denominator. So if you're ever stuck and you're supposed to add or subtract, this is like adding fractions. Okay, so that's something that you can do if you ever get stuck. Think about that list and rule number 6, which says to add the fractions. Now, am I finished? Well, a couple reasons I know I'm not finished. One, I really don't want to have a fraction like this if I can avoid it. I would rather bring that cosine back up here. But even before that, what's a 1 minus cosine squared? Remember, I know that if sine squared theta plus cosine squared theta is 1, then if I would subtract that, what is 1 minus cosine squared theta? Well, it's sine squared theta. So I'm going to replace that with this right here. So there's my 1 minus cosine squared theta. I'm going to put a sine squared theta in its place, copy down the cosine squared, and wait, what's sine over cosine? If sine over cosine is tangent, and all the squared means is that I have 2 sines and 2 cosines, then I should have tangent theta, or tangent squared theta. And that's my number 11. And all this right here was just me thinking out to the side. Now, I hope at some point you know these identities well enough that when you see a 1 minus cosine squared or 1 minus sine squared, you'll know that and you'll be comfortable with it. But if you need to write it out and kind of see what it's equal to be careful, do that. Okay? All right, look at number 13. All right, so number 13 says you have a 1 plus a tangent squared alpha in the numerator, and you have a tan squared alpha in the denominator. Now, I'm going to show you 2 ways you can do this. The first way you might do this is go, wait, I recognize 1 plus tangent squared. I know that 1 plus tangent squared alpha is secant squared alpha. That's a Pythagorean identity. So I'm going to take that top part and I'm going to change it to secant squared of an alpha, and I'm going to change that tangent, or I'm just going to leave the tangent squared alpha where it is. Now, when I look at this, I go, I have no idea what that is. All right, so I'm going to do basically rule number 2, which is change everything to sines and cosines. Okay, now again, you could do this multiple ways. I'm going to change the secant right where it is to a 1 over a cosine squared, and I'm going to change the tangent squared to a sine squared over a cosine squared, because those are identities I have. And then if you understand fractions well, you'll see that I can cancel both of those cosines and I'd be left with 1 over sine squared. But if you don't see that, just keep the top where it is. And how do you divide by this fraction? You multiply by its reciprocal. And then once you do that, you can see that they cancel. But if it were me, I would have canceled them right there, and I would have had 1 over sine squared, just like I do right now. And then 1 over sine squared, am I finished? Well, it's pretty good. Sorry, I don't know why x suddenly appeared there. That's a theta. Sorry, theta. I'm sorry, not theta, alpha. Alpha. 1 over sine squared. Our first rule says try to represent it in the numerator. So what is the sine squared in the denominator? Because it's a reciprocal of that is cosecant. I'm going to put a cosecant squared alpha in the numerator. Now that's one way to do it. Let me show you another way. Another way is to take this right here, this original problem, and think about it as 1 over that plus 1 over this. And if I put 1 over tangent squared, and a lot of people don't even write this, but I'm going to write it for you, and then tangent squared over tangent squared is 1. And tell me, what is 1 plus tangent squared? 1 plus tangent squared is cotangent squared. Are you with me? And I have an identity. Not only do I have this identity right here, but there's another identity that says 1 plus cotangent squared alpha equals cosecant squared alpha. And what do I have right here? 1 plus cotangent squared alpha. So this right here is equal to cosecant squared alpha. And look, I did it with much less work than all of that. And if you can get it done more quickly, great, which is a great example of why you don't just trust the textbook. I will know on your test. Actually, I will know. It'll be hard for me to give you a good test here in a lot of ways, because I'm gonna have to really be creative in a lot of ways, because your process will be really different depending on kind of which strategy you use. So it's very likely that I may even have you turn in your work or submit your work with this, because your processes are going to look different depending on who you are. Anyway, whatever. That's number 13. Let's look at number 15 here. All right, number 15 says cosine squared of 50 degrees plus sine squared of 50 degrees. Now, a lot of people initially go, oh, wait a minute, I can't do cosine squared of, or cosine of 50 and sine of 50. And by the way, if I were to enter this in my calculator, remember what this means. What it really means is cosine of 50, get that answer, then square it. This means sine of 50, get that answer and square it. But on the test, you'll be doing this with a calculator, so you actually could probably type that in a calculator and it would spit out the answer 1, which means I probably won't give you a question like this. But the point is, you have a Pythagorean identity that says sine squared theta plus cosine squared theta equals 1. And what that means, if you're adding a sine squared and a cosine squared, if you're adding it and the angles match, it doesn't matter what the angles are. If they match, it's always equal to 1. Well, sine squared, cosine squared, angles match, this is equal to 1. So even though I don't know what cosine of 50 or sine of 50 is off the top of my head, I don't know. I have no idea. But they do match. Those angles match. I am adding the squares. I know that's going to be equal to 1. All right? And then looking at number 17. Number 17 right here says cosecant squared of angle T minus cotangent squared of angle T. Well, that looks familiar to me. When I think about those squared values, remind me of a Pythagorean identity. And which Pythagorean identity includes cotangents and cosecants? Well, it's the one I wrote up there earlier. It's 1 plus cotangent squared theta equals cosecant squared theta. Well, can I use this to help me do that? Let me see. I've got a cosecant that's positive. That's already positive. What would happen if I subtracted that cotangent from both sides? It would go away there, but appear here. So what does that tell you about cosecant squared minus cotangent squared? It tells you no matter what, as long as those angles match, it's equal to 1. So all of this is equal to the number 1. And if you're thinking to yourself, if in doubt, put the number 1, well, on this homework assignment, that would have worked out pretty well for you. But again, for me, guys, it's the process that matters. It's not just your answer. But if you are getting the answer right, more than likely your process is okay, even if it's not the same as mine. All right? So that was number 17. Let's scroll on down and look at number 19. Number 19 said, all right, we've got this sine of angle alpha times a cosine of angle alpha, and all of that's divided by 1 minus the sine squared of angle alpha. Now, I hope what's jumping into your brain right there is that denominator. I have a Pythagorean identity that is this: sine squared of theta plus cosine squared of theta equals 1. And I can see the 1 minus sine squared in this. See, if I subtract that from both sides, I get 1 minus sine squared theta, right? So if that can be representative of this, what would this part be equal to? It'd be equal to cosine squared, not theta, but cosine squared alpha. So I'm going to rewrite that denominator as cosine squared alpha, and then just drop the numerator down. All right? Okay, now, when I look at this fraction, I think, oh, well, now I've got a cosine on the top and the bottom. I could cancel one of those with one of those, and that leaves me a sine of alpha over a cosine of alpha. And what do you know about sine of angles over cosine of angles? They're the same thing as a tangent of that angle. All right? All right, look at number 21. Number 21 says you have the secant of x minus the sine of x times the tangent of x. All right? So on number 21, again, I look at this and I'm like, what the heck? I don't recognize this at all. And if I don't really know what to do with it, and I don't see any fundamental identity right there that jumps out at me, or a Pythagorean identity, or I don't have fractions. I think, well, maybe I could change it all to sine and cosines. And if I do that, maybe something will come to mind. So what is a secant? It's a 1 over a cosine. And a sine is already in terms of sine and cosine. And what is a tangent? It's a sine over a cosine. So what do I end up having here? I have a 1 over a cosine of x minus a sine squared over a cosine of x. And now that I have these common denominators, I could add these fractions by keeping the denominator and subtracting the numerators. I say add loosely, subtract the numerators. Now, am I finished? No, but what do I have? Just like I did in number 19, you have a 1 minus sine squared of the angle. And we know that that's equal to cosine squared of the angle. So right here, if I have a 1 minus sine squared of x, that's equal to cosine squared of x. Carry over the bottom, and then what happens? Sorry, that's not a squared. All right, carry over the bottom, and now what happens? I can cancel one of those cosines with one of those cosine x's, and I'm left with cosine of x. Because remember, cosine squared x is the same thing as me doing this, but I don't do that because it's bad form, right? So I can just cancel one of those with one of those, and I'm left with cosine x. Who knew? All right, 23. 23 says, or you're given 1 minus sine squared of phi, the Greek letter phi, over 1 minus sine of phi. Now let me show you one of the huge mistakes I see. One of the huge mistakes I see is people go, oh, I can cancel the 1 out, and I can cancel one of the sines out, right? And then they end up with something like negative sine theta. Now your answer, and oh, sorry, that's not the whole answer. Then I'm the question, it's minus 1. Well, that's not going to be your answer. If you end up with negative sine theta minus 1, you got destroyed. Now, you know you can't cancel like that. That would be like me doing this. That would be like me going 2 plus 4 over 2 plus 6 and canceling that out and canceling that out and getting something like 2/3 or whatever. You know that this answer is not equal to 2/3. It's not even equal to, even if you canceled and put a 1 there, it's not equal to 3/4, is it? Actually, it is equal to 3/4, but that, good gracious, you got to be kidding me. That's hilarious that this actually ended up that way. But, and the reason, you know why it did, is because what I really did is I factored a 2 out and canceled it all out. So that's just a massive coincidence because these are 2s. Let me give you another one. What about this? 1 plus 4 over 1 plus 6. If you cancel that out and cancel that, so actually, miraculously, that was, sorry, but this is a terrible way to think. If I were to try to cancel here, check it out. Even if I do leave a 1 there, do I really get 3/4? No, you knew this original problem was 5/7, which doesn't even simplify, does it? And even if I didn't leave a 1 there, is it equal to 2/3? Are these right? Absolutely not. So don't do any canceling that when you have pluses or minuses. Don't do it. Okay? So please don't do any of this kind of craziness. The only time you can cancel is if it's a product on the numerator and the denominator. All right, so what do I do? Well, if you get stuck on something like this, if you look at number 5 on my list of things that might help you, it's factor. And if I factor something, maybe something will cancel, maybe something will, you never know. And that was one of the strategies we did anyway when we had fractions. The part of PEMDAS is to divide, but to divide, I have to have a factor. So this is a difference of 2 squares. So what if I factored it as that and that? All right, we know how to factor a difference of 2 squares. I know it's a little ugly, but it's 1 minus sine theta squared. So 1 minus sine theta, 1 plus sine theta. And the bottom's already 1 minus sine theta. All right, and then what do I see? Oh, now I can't cancel the signs, but I can cancel the 1 minus sine with the 1 minus sine. I can cancel that entire factor out. And what am I left with? 1 plus sine of phi minus 1, and now your 1's subtract, and I'm left with sine of phi. You track with me? All right, so that was 23. We're going to jump over to 39. All right, so here's number 39. And 39, we have the tangent of t plus the cotangent of t over the secant squared of t. Now, I really want to talk about this one because a lot of people mess this up based on what I just showed them in a prior problem. And on this particular problem, the mistake people make a lot is they take this cotangent of this angle and they go, oh, I could change that cotangent on the top to a tangent on the bottom. And then I could just cancel those out. Well, that'd be kind of like me doing this. If I'm trying to add 1 plus 3, that's like, think about this. We know that this value right here is 4. But that would be like me saying, oh, I can take a 3 on the bottom and I can change it to a 3 on the top and change it to a 1/3 on the bottom. And now I have 1 divided by 1/3, which is 3. Okay, well, we know that that's not true, is it? Because this original problem was equal to 4. So this mentality didn't work. Why can't I take a number and make it a reciprocal on the bottom? And the reason why it didn't work is because there was a plus. And it's also true if there's a minus. Now, if it was a times right here, then I can do that. A 3 on the bottom, because this now is equal to 3 over 1, which is 3. And a 3 on the top can be a 1/3 on the bottom. And that would still be true, right? So it's true when you're multiplying, but not when you're adding. Well, I'm adding over here. So I just can't move this to the bottom. Now, could I move the secant squared up? I could, but if I change the secant squared on the bottom to a cosine squared on the top, it has to be on the outside of the whole top. So basically, I would have to then distribute it in maybe. So what I'm going to do, because I'm kind of confused here, is I'm going to go back to that rule number 2, which just convert everything to sines and cosines, but I'm going to do it right where it is. So I'm going to change tangent to sine over cosine, right where it is. I'm going to change cotangent to cosine over sine, right where it is. And I'm going to change secant to 1 over cosine, but because it's squared, I'm going to square it. Okay? And now this has become this. And now, to divide by a fraction, what do? You take it and you multiply the numerator by the reciprocal. So I'm going to multiply by cosine squared t over 1. Now, all I have to do now is distribute this in, and it'll be cleaned up at least a little bit. So when I distribute that in to that and that, what happens? Well, this times this, tell me what happens. Anybody? I'm going to cancel. I just said anybody, like I'm waiting for you to respond. I'm going to cancel one of the cosines, and I'm left with 1 cosine times 1 sine. So there's my sine, there's my cosine. And here, I don't get anything canceling, so I get cosine cubed t over a regular sine t. All right? And when I look at this, I'm like, what in the world is happening here? So you may think that this is not progress, but I actually think it is a lot of progress. And I'm going to go, if I think of another way to do this, I'll show you. Well, at this point, I at least have it down to where I can add these two fractions, and I can do that by finding a common denominator. So what would I have as a common denominator? I would need a sign here, but if I'm going to multiply the bottom by a sign, I would have to also multiply the top by a sign, which would make that sign squared. Now, you may not think you're getting anywhere, but I think I actually am getting worse. Check this out. Now, when I add these together, check out what I have. I get all of that over a single sign. Now, anybody got any ideas? Well, one of the things on your sheet, if you look at it, is to factor the polynomial. And when I look at this right here, I see that there's a cosine that they both have in common. And what would happen if I factored out that cosine? If I factor out one of those and one of those, I'm left with sine squared plus cosine squared on the inside. And what is sine squared plus cosine squared on the inside? That's right. All of that's equal to 1. And now I'm left with cosine over sine, which we know is cotangent. All right? So that was kind of an ugly looking problem, but it is something that I can actually do. All right, now I'm going to show you another way that you could do it. I'm going to come back to the original problem, and this way might be easier. If I come back to this, what would happen if I put tangent over this and cotangent over that? All right, so I'm going to write that down here on the bottom. I'm going to put the tangent over the secant squared. And then I'm going to put the cotangent over the secant squared. All right, now let's try to simplify this. This is another way. Well, if I do that, now these are their own separate fractions. So now if I have a secant squared on the bottom, I could just bring it up because it's not joined to anything else, right? It's its own separate fraction. I can bring that up and just put it in the numerator as a cosine squared t. Over here, I can bring that secant squared up and put it in the numerator as a cosine squared t. And then I can change everything to sines and cosines and pray something nice happens. So check it out. I'm going to change that to sine over cosine. I'm going to leave that how it is. And I'm going to change that to cosine over sine and leave that where it is. And look what I have here. If I cancel stuff right here, if I cancel a cosine out, and here I can't cancel anything out, I get sine of t cosine t plus cosine cubed t over sine of t. Now you may think, how is this helpful? Well, look, in one step, I'm going to be right back where I was in the other problem. To find a common denominator, I'm going to put a sine t on the bottom here, balance it with the sine squared, and if you look at this, this right here is exactly what I had right here in the problem before. Okay, so at that point, I can add my fractions, factor out a cosine, cancel that because it's Pythagorean, and I'm left with cosine over sine, which is cotangent. So different approach, same result in the end. I just didn't want to recopy all of that down again. All right, so more than one way to skin a cat. That's just one of them. Okay, so after 31, here is number 41. All right, so number 41, I have a cotangent of theta, and I'm multiplying by a cosine theta times a tan theta plus a sine theta. All right, now what in the world? I don't really see anything that jumps out at me. I know that PEMDAS says to multiply, so I could potentially multiply this in. I don't know if that's going to look that great when I do, but I might do that. But one thing I could do that might help me see more clearly is just to change everything to sines and cosines. So you'll see I'm using that number 2, convert to sines and cosines, a lot when I'm in trouble or when I don't feel comfortable about maybe where to go. All right, so that's cosine over sine. I'm going to leave this cosine there. That's sine over cosine. And it's one big fraction because I'm multiplying them together, right? And then this is just a regular sine. Okay? Now you might look at this right now and go, wait, cosine over cosine cancels, right? And now what do I have left? Sine theta plus sine theta. And if I have sine theta plus sine theta, what do I get? 2 of the sine thetas. It's like x plus x is 2x. Sine theta plus sine theta is 2 sine theta. But you still have this on the outside, right? So what do I get if I have a cosine over a sine times a 2 times a sine? Well, again, these are like fractions. I can cancel the sine thetas out, and I'm left with cosine theta times 2. Now, nobody writes cosine theta times 2. Nobody does that because people start thinking, oh, does that mean cosine of 2 theta? Don't do either of those. If you have a coefficient left in your problem, swing it out to the front. You don't write stuff like x times 2. You write 2x. We'll do the same thing with trig functions. So I'm going to write that as 2 cosine of theta. All right, a couple more. 43. All right, so 43 says tangent squared theta. Actually, tangent squared x over secant x plus 1. Now, I'm going to show you 2 ways to do this. I'm hoping that one of them sticks in your head and you go, oh, sounds good. I look at this problem and I'm like, the thing that jumped out at me, which may or may not jump out at you this early in the game, but hopefully will eventually, is I know a Pythagorean identity that actually has a tangent squared in it and a secant squared in it. And I'm going to write it over here. If to remind you, it was that Pythagorean identity right here. Now the problem is, this is clearly not that, okay? But because it has the same idea going on there, I'm thinking, I bet there's a relationship. Now, one thing I could do, this is strategy 1, is I could replace the tangent squared with, if I think about it, if I subtract 1 over, I could replace it with a secant squared x minus 1. So here's my first option. I could replace it with secant squared x minus 1. And I'm doing that because the secant squared x plus 1 on the bottom kind of looks familiar to this. And then when I get to here, again, I can't cancel those secants because they're connected to the ones by addition or subtraction. But what I could do with the top is, well, what does rule number 5 say on my sheet? Factor. And this is a difference of two squares. It's like an x squared minus 1. And an x squared minus 1 would factor into x plus 1, x minus 1. Well, a secant squared x minus 1 factors into secant x plus 1, secant x minus 1. And then here's my denominator. All right? And now I can say, oh, well, now that they are factors, I remember I can't cancel the secant out, but I can cancel the whole factor with this whole factor. And that gets rid of not the secant and the 1, but the secant x plus 1 and the secant x plus 1. And then what do I have left? I have a secant x minus 1 plus 1, which now adds whatever it subtracts together and leaves me a secant of x. All right, so you could have treated this like a factoring problem. I replace it with a Pythagorean identity at the get-go, and I know to do that because I recognize that this Pythagorean identity includes a secant squared, and there's a secant there, so I have some hope there. But there's another method I could use. I'm going to put it right here. I'm going to recopy this problem. And the other method I've actually included in one of your strategies as a different option, and you'll see it down at the very well, almost the bottom. It's number 7. It says create a monomial denominator, and you do this by rationalizing it. So it's not really rationalizing, but it's kind of. You remember how when you had something like, a fraction like root 2 plus 1 on the bottom, you'd multiply the top and the bottom by root 2 minus 1? Remember doing that to rationalize the denominator? Well, I'm going to do that here, but instead of multiplying by a radical expression with a different sign, I'm going to multiply by a trig expression with a different sign. So check this out. I'm going to leave the top alone for now, and I'm going to multiply the bottom by secant x minus 1, and then to balance it, I've got to keep it honest by doing the numerator as well. All right? Now, what does that give me? Now, before you go and start foiling stuff out here, don't do that yet, and you'll see why. Don't do it. I'm just going to leave that multiplied together. I'm not going to distribute the tangent squared in. What do you get on the bottom? On the bottom, I get secant squared, and then the outside and the inside as you foil cancel, and then minus 1. And guys, what's secant squared x minus 1? Well, back from this, what is secant squared x minus 1? It's tangent squared x. So I can replace the denominator with a tangent squared x, and this is why I didn't distribute it in. Now what can I do? I can cancel out the tangent squared x's. Don't forget that plus 1 there. And what do you have left? I have secant of x minus 1 plus 1, and then again, they cancel. So two different strategies to get the same result. If you think about it, they're kind of similar, but one requires factoring to cancel. One requires rationalizing. And when I say creating a monomial, look what I did. I took this binomial, and when I rationalized it, I ended up with an expression that turned into a monomial. And now the monomial part cancels. Okay? So that's a strategy. Either you're going to end up basically using rule number 5 and factoring that to make it, replacing that and factoring it to make it cancel, or rationalizing to get a monomial to make it cancel. But they're in the same vein of ideas. All right, that's 43. Let's take a look at 45. All right, number 45 right here says you have this tangent of theta, and you're dividing by 1 plus secant theta, and then you have a 1 plus secant theta on the top here, and you're dividing it by a tangent theta, and it wants you to simplify this. Now, a lot of people make the mistake of canceling the tangents and canceling that. Why can't I do that? That's right. This is not multiplication. This is addition. So the only way to add these is to find a common denominator. So again, I'm going to show you two strategies. So the first strategy is, you know what? I'm just going to flat out find a common denominator. So if this is what I have over here and this is what I have over here, I'm going to multiply this side by tangent theta on the top and the bottom. And I'm going to multiply this over here by 1 plus secant on the top and the bottom. And now I have a common denominator, don't I? Right? Tangent theta, 1 plus secant theta. Now I do have to clean up the top part, so let's do that. Here, I have one denominator now, tangent theta, 1 plus secant theta. And then I have tangent squared, which I can add to whatever I get from this. Now, what do I get from this? This is not a difference of two squares. So when you FOIL this guy out, I actually get 1 times 1, and then you get positive secant theta, and then another positive secant theta, and then finally a secant squared theta. Okay? So all of that gives me 1 plus 2 secant theta plus secant squared theta. So at first glance, you're like, what in the heck is this? This is a mess. All right, so I'm just going to hold off there, and I'm going to go, Again, I'm not claiming this is the best way to do it. This is just a way to do it. Now, when I look at this, I actually see a Pythagorean identity. What is tangent squared of theta plus 1? That's secant squared theta, isn't it? That right there is a secant squared of theta, which I can now add to this secant squared of theta. Okay? So when I combine all that together, I get a secant squared theta plus 2 secant plus another secant squared theta, which is 2 secant squared thetas plus 2 regular secant thetas all over a tangent theta and a 1 plus secant theta. Now, I don't know about you, but to me, this doesn't look a whole lot better, but I do see a little hope. And this gets me to, I've used all kinds of rules here. I have multiplied stuff out. I have found a common denominator and tried to add fractions. And now I'm looking at this and going, you know what? What if I tried factoring? If I factored the 2 and one of the secants out, what do I have left? I have 1 secant remaining. And here I have nothing but the number 1 remaining. And there's the money right there. What do I end up with? I end up with a match here and here. I know they're in a different order, but it's the same thing. So that cancels, and now I'm almost home free. I have 2 secant theta over a tangent. And at this point, couldn't I maybe change everything to sines and cosines? Let's check it out. I'm going to, I'm right here. I could change in the numerator, I could change the secant to a 1 over a cosine. The denominator, I could change that to a sine over a cosine. And at this point, it would be great if you went, oh yeah, because I'm dividing, I can cancel these cosines out. And if I did that, I would be left with a 2 and a 1 times a 1, all of it over a sine. And what's 2 over sine? That's 2 cosecant theta. So that's one way to go. The other way to do is how do you divide by a fraction? You multiply by its reciprocal, right? Which cancels that out and leaves me a 2 times 1 over a sine of theta, and a sine in the denominator is the same thing as a cosecant in the numerator. And either way, you get where you want to be. So if you're looking at these and going, man, these take a lot of time and a lot of effort, they do, and you're seeing them for the first time. The more you get exposed to them, the better. And you will see that eventually these will actually become things that are not as awful as you are maybe feeling right this second. So last but not least, let's look at 47. Okay, 47 says, all right, I've got this fraction, cosine of angle t plus sine of angle t squared plus cosine of angle t minus sine of angle t squared. Now remember, to square a binomial, you don't square each part. You would have to write out twice and FOIL it, right? Now what you can do is, remember what you did with x plus y squared? You squared the first term, all right? You went that times 2, and then you squared the last term. So that's how you square something. Well, I can do that here. Instead of writing it out twice, I could square the first term, cosine squared t. I could go that times 2. And then I could square the last term. So that's the trinomial I get when I square this binomial. All right, now I could also do the same thing with this. I could square the first term. And then I could go that times 2, which gives me negative 2 cosine t sine t. And then finally square the last term. But don't make the mistake of squaring each part. You can't do that when you're adding or subtracting, or where you have a binomial or trinomial or something like that. You have to use this rule, or I guess you could use the 1, 2, 1, the 2 row of Pascal's triangle to do it. But I just know my little squaring binomials rule. And then look, you're home free. Look at this. These cancel. And somebody tell me, what is cosine squared plus sine squared? Well, sine squared of an angle plus cosine squared of an angle is 1. And then over here you have a sine squared of an angle plus a cosine squared of an angle, which is another 1. And 1 plus 1 is 2. All right. So hopefully these were a learning experience for you, and you're doing okay on these. If not, practice makes better. But I think you need to know these 8 steps. And you'll notice the very last one I haven't mentioned. It says, don't just give up and stare at the problem. Don't do like Kevin Hart and go, what? You got to look at these and you got to try something. And if you just try something from this list, usually a door opens kind of like a rat in a maze. They don't know where they're going, but they sniff around. You just got to sniff around some and experiment some. And sometimes you're going to get lost and you're going to go in a bad direction. Try something else. Don't be afraid of it. Don't assume the position. And I think you'll be okay. All right. Thanks, guys.